my solenoid, okay, and there's my magnetic field lines moving from north to south. And so as I move this magnet through, look at the light bulb, I am actually inducing an EMF, and hence the light bulb, this current, the electrons are moving, and we are creating, and we are having the light bulb come on. Okay, and so what we are going to learn about is this law here, which is called Faraday's law. Okay, after Faraday, who discovered it, Faraday's law of electromagnetic induction. The EMF induced is directly proportional to the rate of change of magnetic flux. And so this is a very important equation that we are going to be looking at. This refers to induced EMF, okay? Capital letter N stands for number of windings. This is change in phi, or change in flux, and time. And so the first thing that we're going to look at, we're going to unpack everything here. But the first thing that we are going to look at is the number of turns, okay? And if I look at the number of turns, let me just go to the other simulation. There we go. All right, so you can see that here I have just one turn, okay? But if I go now and I want to look at the voltmeter, okay? Not much EMF is induced. But if I make my number of loops, let me just make it here. If I increase the number of turns to 3, now I want you to look up here and look at this. Okay, can you see that it is increasing? I just want to do it here with the mouse. Okay, so you can see it is going much higher. The voltage is much higher. And if I change this to a bulb, okay, you can see that the brightness is definitely more. So therefore, if I have more turns, the EMF induced is greater. And so we looked at the first one, which is the number of windings in the coil. Okay, so if I look here also, that's why I preferred to use this one, which has 360 turns, okay, versus this one here, which has too few turns to induce the current. Now we're going to look at the next one, and we're going to unpack this rate of change of flux. And so if I look back here at the simulation, okay, this simulation, I'm going to do this a bit slower, okay, and I want you to focus on the brightness of the light bulb here, right? So I'm going to go very slowly. Can you see? Not very bright. But when I go faster, can you see that? The rate of change of flux is increasing. And so let's just go back to this equation here, and you can see what kind of relationship is there between EMF and time. You can see it's an inverse. So if I decrease the time and I go faster, my induced EMF is going to be greater. Okay, and so we can see that that's how I'm increasing my EMF, by making the rate of change of flux. So let's just go over this one more time. When I decrease time, my EMF is going to increase. There's an inverse relationship. But if I look at EMF, is directly proportional to the rate of change of flux. So here, there's a direct proportion. The rate of change of flux is changing, therefore EMF is going to also change and increase. Okay, we'll come back to this negative sign just now, but let's go further on to flux and what does flux mean, okay? And so if I look here, flux is actually like when my magnetic field lines, how it is cutting through the area of the coil, how it's cutting through the area of the coil, okay? And so the field lines, how is it cutting through the area of the coil like this? There's the field lines, and how is it cutting through? Okay, so magnetic flux refers to the number of field lines that cut through the coil. If I look at the next thing now, we're going to break down flux into this equation where B stands for magnetic field lines and area, and then we're going to break this further down into the cos of the angle. Okay, so what does cos of this angle is? This angle is between the magnetic field lines and the normal of the conductor. So if I had, for example, this here as my north and this here as my south facing magnet. So my north facing, my south facing. You can see the magnetic field lines are going straight like this, okay? And there is my conductor. The conductor has, there's a conductor, the conductor has a normal. Remember, a normal is always perpendicular, okay? So there's the normal and it is perpendicular. But I want you to look at this. There's the normal like this and there's the field lines. Can you see that it is perpendicular? And so cos 90 is going to be equal to, I want you to take out your calculator and tell me what is cos 90 equal to. Let me also take my calculator out. Okay, and so cos 90, what do we get? It is 0. And so here we are going to get the minimum. So it's a minimum flux. But if I look at this angle now, north to south this way, all right, there comes the conductor, and the conductor has its normal. So there's my conductor, the conductor's like this, and there's my normal like that. The normal and the magnetic field lines are in the same direction. And so this is going to be cos 0. And if you put cos 0 onto your calculator, you will see that cos 0 is equal to 1. And so this is maximum flux, and this is going to be minimum flux. And any angle between that is going to still give us an EMF induced, but we want it always to be where the conductor is going to be perpendicular to the magnetic field. And so the last thing that we're going to talk about here is this negative sign, and this negative sign has got to do with Lenz's law, and we'll talk about Lenz's law another time. Thank you.